And now in this lecture we'll answer on two questions. The first question, we find out the area of this green shape. In the second question, we find out the length of line segment AP is equals to x using two different methods. We start with the first question. In the drawing, we have this semicircle. You know that BC equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10 units. PC equals to 8 units. This is angle ABC. This is a right angle. And our task is to find out the area of this green shape. So first of all, we join points P and B together by straight line. By joining points P and B, we create peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So please click on rule 5. According to rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of the circle. This is peripheral angle AEB that subtends on AB, that is the diameter of the circle, and therefore peripheral angle AEB must be equal to 90 degrees in its size according to this rule, rule 5. We can actually implement rule 5 in our drawing. One goes in our drawing. We have peripheral angle BPC that subtends on BC, that is the diameter of this semicircle, and therefore according to rule 5, peripheral angle BPC must be equal to 90 degrees in its size. So in the next step, we implement the Pythagoras theorem on this right angle, triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. So in the right triangle BPC, BC is the hypotenuse of the right triangle BPC, therefore the square of the hypotenuse is BC square, and BC square must be equal to PB square plus PC square. Okay, again, according to the Pythagoras theorem, in the right triangle PBC, BC square equals to PB square plus PC square. The hypotenuse BC equals to 10 units in its length, therefore BC square is 10 squared, this is 100. And it is equals to PB square. PB is the missing side, so we leave it as it is. So it is PB square plus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So in total, we should find out that equals to PB square plus 64. Here we subtract 64 from this equation, and we get that PB square equals to 100 minus 64. 100 minus 64 is 36. PB square equals to 36. Here we take a root out of this equation, and finally we get that PB equals to the square root of 36. The square root of 36 is 6. So the missing side PB equals to 6 units in its length. This is the missing side PB that equals to 6 units in its length. It is given us the question that AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AC at point P? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right triangle APB, we define the size of angle ABP, this angle as alpha. So this angle equals to alpha according to our definition. So alpha plus 90 degrees plus the size of this third missing angle, in total it must be equal to 180 degrees according to the rule that says that the sum of the angles in the triangle is equal to 180 degrees. Therefore this third missing angle must be equal to 90 degrees minus alpha. It is given us the question that the big angle ABC is the right angle. Angle ABC equals to 90 degrees in its size. So what is the size of the missing angle, angle PBC? From the drawing it is very easy to see that angle PBC must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is equal to 90 degrees. That is the size of the big angle ABC according to what is given as the question. Therefore this missing angle must be equal to alpha. So in the right angle PBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that those two right angles are similar to each other according to angle similarity rule. That is to say, we prove that the right angle ABB is similar to the right angle BPC according to angle similarity rule. So, why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the angles of the right angle APB are correspondingly equal to all the angles of the right angle PBC, and therefore those two right angles are similar to each other according to angle similarity rule. So right now, we should prove that the right angle PBC we prove that the right angle PBC is similar, this is the sign of similar, to the right angle PBC and to the right angle APB according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right angle APB over side BC of the right angle PBC is equal to side AP of the right angle APB over side BP of the right triangle PBC. Actually, PB is the common side that belongs to both triangles. And also, that side PB of the right triangle APB is equal to side PB of the right triangle APB over side PC of the right triangle PCB. Okay, so we derive that AB over BC equals to AP over PB equals to PB over PC. And then in the numerator, in each numerator we have the sides of the right triangle APB, and in each denominator we have the sides of the right triangle PBC. So in total, if we found out that AB over BC equals to AP over PB equals to PB over PC. AB is the missing side, so we leave it as it is. Over BC. BC equals to 10 units in itself, according to what is given as the question. And it is equals to AP. AP is the missing side, so we leave it as it is. Over PB. PB is 6, according to what we have already found out. And it is equals to PB again, it is 6. Over PC. PC equals to 8 units in its time, according to what is given as the question. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions are equal to each other. Therefore, we get equation 1 from those two expressions. According to equation 1, we get that AB over 10 equals to 6/8. AB over 10 equals to 6/8. Here we will multiply this equation by 10, and we get that AB equals to 10 times 6 is 60 over 8. Here we will divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, and 8 over 4 is 2. So in total, we should find out that AB equals to 15 halves. AB equals to 15 halves. So I can write down here that the drawing this is side AB, that equals to 15 halves, 15 halves in its length. Likewise, those two expressions are also equal to each other, so we get the second equation from those two expressions. According to the second equation, AP over 6 equals to 6/8. So here, so according to the second equation, AP over 6 equals to 6/8. Here we multiply this equation by 6, and you get that AP equals to 6 times 6 is 36 eighths. Here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, and 8 over 4 is 2. So in total, we should find out that AP equals to 9 halves. AP equals to 9 halves. In the next step, we define the center of this semicircle. This point is point O. The diameter BC is 10, therefore the radius is 5. BO is 5, the radius BO is 5. The radius OC is also 5. We join points P and O together by straight line. PO is also the radius of this semicircle, that is 5. In the next step, we define angle POB. This angle is theta. So I present to you the law of cosines, and we implement the law of cosines. This triangle POB. Actually, the law of cosines is true in any triangle. This is triangle ABC, that could be any triangle. Side AB of triangle ABC equals to A unit in its length, side AC equals to B unit in its length, side BC equals to C unit in its length. This is angle BAC. The size of this angle BAC is theta. So in this triangle ABC, the following equation is true. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, we will implement the law of cosines in this triangle POB. According to the law of cosines, this triangle POB, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. Repeat again, according to the law of cosines, this triangle POB, the following equation is true, that cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So cosine theta equals to 5 squared. 5 squared is 25, plus 5 squared, that is 25. 25 plus 25 is 50. Minus 6 squared. 6 squared is 36, so it is minus 36 over 2 times 5 times 5 is 50. 50 minus 36 is 14 over 50. So in total we should find out that cosine theta equals to 14 over 50. Our task is to find out the value of theta itself. So I'll give you an example. We know that the inverse function of a square is a root. Okay, if we take number 3 and we square it, 3 squared is 9. Now, in order to get number 3, that is the number before the operation of the square on it, we have to operate the inverse function of a square that is a root on the result 9. And the square of 9 is 3. That is to say, the inverse function cancels out the operation of the function, because we operated the function square on number 3 and the result is 9. Now, if we want to get back number 3 again, we have to operate the inverse function of a square that is a root on the result, that is 9, and the square root of 9 is 3. So likewise, we operated the function cosine on theta, and the result is 14 over 15. In order to get back angle theta again, we have to operate the inverse function of cosine, that is r cosine, on the result, that is 14 over 50. In this way, we get angle theta itself. We get angle theta itself, that is to say, angle theta before we operated the function cosine on angle theta. So r cosine 14 over 50 is equal to 73.73 degrees. You can find out the value of r cosine 14 over 50 by using any simple calculator. Okay, it must be a scientific calculator, but okay. So r cosine 14 over 50 is equal to theta, and angle theta itself equals to 73.74 degrees in its size. So found out that this is angle theta, and the size of angle theta is 73.70 degrees. In order to find out the area of the green shape, we have to find out, first of all, the area of this segment, segment BP. So what is the area of segment BP? The area of segment BP will be equal to the area of sector BOP, minus the area of triangle BPO. So repeat again, we actually found out that the area of segment BP is equal to the area of sector BOP minus the area of triangle POB. So what is a sector? A sector is a portion of a circle with two radii and the arc that between the two radii. And again, the green shape AOB is sector. Sector AOB consists of two radii and arc AB that is between the two radii. Angle theta is the angle between the two radii or the angle between the legs of sector AOB. The area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the circle, over 360 degrees. Repeat again, the area of this sector AOP equals to pi r squared times theta over 360 degrees. So we use the new formula in order to find out the area of this sector, sector POB. So the area of sector POB must be equal to pi r squared, that is the area of the circle that contains the sector, times 73.74 degrees, that is the angle between the legs of the sector, over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25. Pi r squared is 25 pi times 73.74 degrees over 360 degrees. So in total, the value of this expression is equal to 16.088 square units. So if you found out in total that the area of this sector BOP is equal to 16.088 square units. Minus the area of this triangle BOP. Triangle BOP is an associated triangle because side BO equals to side PO equals to 5. The base BP is 6. BP equals to 6 according to what we already found out. In order to find out the area of this triangle, associated triangle BOP, from the vertex O, we draw perpendicular on the base PB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and the base PB. This point is point M. We have the rule that the perpendicular to the base of an associated triangle bisects the base. The base PB is 6, therefore each half equals to 3. PM equals to 3, and MB also equals to 3. The area of this triangle, the associated triangle of BP equals to the base, that is BP, times the height to the base, that is MO. Why MO is the height? Because it's creates 90 degrees with the base PB divided by 2. So we have to find out the height MO. We'll implement the Pythagoras theorem. In order to find out the height MO, we'll implement the Pythagoras theorem on the right triangle PMO. According to the Pythagoras theorem, on the right triangle PMO, 5 squared minus 3 squared equals to MO squared. 5 squared is 25, minus 3 squared is 9, so 25 minus 9 is 16, and 16 equals to MO squared. Here we take a look at this equation and find here that MO equals to the square root of 16, that is 4. So MO equals to 4 units in its length. BP is 6, MO is 4 divided by 2. 4 over 2 is 2, and 2 times 6 is 12. So in total, if you found out the area of this associated triangle PBO is equal to 12 square units. So the area of the sector PBO that is 16.088, minus the area of this associated triangle PBO, that is 12. In total, it is equal to 4.088 square units. So in total, we found out that the area of segment PB is equal to 4.088 square units in its size. Our task is to find out the area of this ring shape. So what is the area of the ring shape? The area of this ring shape must be equal to the area of the big right triangle APB minus the area of segment PB. Again, the area of this ring shape is equal to the area of the right triangle APB minus the area of this segment VP. So already know the area of the ring shape equals to the area of the right triangle APB minus the area of this segment BP. Repeat again, the area of the green shape equals to the area of the big right triangle APB minus the area of segment BP. What is the area of this right triangle APB? It is equal to the base AP times the height PB over 2. So already know the area of the right big triangle APB it is equal to the base AP times the height to the base, that is PB, over 2. The base AP equals to 9 over 2, that is 4.5, times the height PB is 6, over 2. 6 over 2 is 3, and 3 times 4.5 is 13.5. Minus the area of this segment BP. We already found out that the area of this segment BP is equal to 4.088 square units, and 13.5 minus 4.088 it is equal to 9.412 square units. So in total, we found out that the area of the green shape, that is the area that we were looking for this question, is equal to 9.412 square units in its size. So if it again, we should have found out that the area of this green shape is equal to 9.412 square units in its size. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question by using two different methods, in two different ways. Our task in the second question is to find out the length of line segment AP that is equal to x. We have to find out the value of x. In the drawing, we have a semicircle. We know that AB equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10 units. In addition, we know that line segment BC equals to 6 units in its length, and AP equals to PC equals to X. Again, our task is to find out the length of line segment AP that is equals to X. We have to find out the value of X. So in the first step, we define the center of this semicircle. This point is point O. The diameter of this semicircle is 10, AB is 10, therefore the radius is 5. The radius AO is 5. The radius OB is also 5. We join points O and P together by straight line. Line segment OP is of course the radius of this semicircle, that is 5. So by doing all those constructions, we get the associated triangle AOP. Right triangle AOP is an associated triangle because side AO equals to side OP equals to 5. And we have the rule that states that in front of equal sides in the triangle, there are equal angles. If we focus on the associated triangle AOP, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle AOP, alpha plus alpha is 2 alpha. Therefore this third angle must be equal to 180 degrees minus 2 alpha. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle APC, triangle APC is an associated triangle because side AP equals to side PC equals to X according to what is given as the question. So in the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But the size of this angle is alpha, therefore the size of this angle must be also equal to alpha because they are equal to each other. Alpha plus alpha is 2 alpha, therefore this third missing angle must be equal to 180 degrees minus 2 alpha, according to the same rule. It says that the sum of the angles in any triangle is equal to 180 degrees. So this third missing angle must be equal to 180 degrees minus 2 alpha. In the next step, I copy the big associated triangle APC and the small associated triangle AOP in a new page, and we prove that those two associated triangles are similar to each other according to angle similarity rule. What is the length of side AC of the associated triangle APC? It is equals to AC in total equals to 10 plus 6, that is 16. So actually, those are the two isosceles triangles that are coming from the original drawing. This is the big isosceles triangle, triangle APC, and this is the small isosceles triangle, triangle APO. So why those two isosceles triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So we should prove that all the figures of the of the big isosceles triangle, triangle APC, are corresponding equal to all the figures of the small isosceles triangle, triangle APO. And therefore, those two isosceles triangles are similar to each other according to angle similarity rule. So write it down. We actually found out that the big isosceles triangle, triangle APC, this big isosceles triangle, is similar, this is the sign of similar, to the small isosceles triangle, triangle APO, according to angle similarity rule. And from the fact that those two isosceles triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big isosceles triangle, triangle APC, or side AP of the small isosceles triangle, triangle APO, is equal to side PC of the big isosceles triangle, triangle APC, or side PO of the small isosceles triangle, triangle APO. AC equals to 16 units in its length over AP. AP equals to X units in its length according to what is given in the question. That is the line segment that we are looking for in this question. And it is equals to PC. PC also equals to X according to what is given in the question over PO. We already found out that PO is the radius of the semicircle that is equal to 5 units in its length. So in total, we actually found out that 16 over X equals to X over 5. Here we will cross multiply this equation and we get that X times X is X squared equals to 16 times 5. So here we take a root out of this equation and we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we actually found out that X, that is the line segment that we are looking for this question, it is equal to either 4 times square root of 5. 4 times square root of 5 is 8.94 units. Repeat again, we actually found out that the length of line segment X, that is the line segment that we are looking for, or the length of line segment AP that is equal to X, is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equal to X is equal to 8.94 units in its length. So we finished with the first method. In the next step, I will present to you how to find out the length of line segment AP that is equal to X using a different method, according to the second method. In the second method, we'll use the rule that we have already used in the first question. The rule is that the perpendicular to the base of an isosceles triangle bisect the base. Again, the perpendicular to the base of an isosceles triangle bisect the base. Triangle APC is an isosceles triangle because side AP equals to side PC equals to X. From the vertex P, we will draw perpendicular on the base AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point P and the base AC. This point is point M. According to the rule that I mentioned, the perpendicular PM bisects chord AC. AC in total equals to 10 plus 6, that is 16. We already found it in the first method. AC equals to 16 units in itself, the base AC. So the perpendicular PM to the base AC bisects base AC. AC in total is 16, so half of 16 is 8. So the first half AM is 8. AM equals to 8 units in its length. We define the center of this semicircle. This point is point O. The diameter AB is 10 according to what is given as the equation. Therefore, the radius of this semicircle must be equal to 5. The radius OA is 5. The radius OB is also 5. In the next step, we will join points O and P together by straight line. OP is of course the radius of this semicircle, that is equal to 5. What is the length of the small line segment OM? OM equals to AM minus AO. So I write it down. The length of the small line segment OM is equal to AM minus AO. So the length of the small line segment OM in total is equal to AM, that is 8, minus AO, is 5. This is the radius of the semicircle, that is equal to 5 units in its length. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. In the next step, I'll copy the small right triangle OMB in a new page and we'll implement on it the Pythagoras theorem. This is the small right triangle OPM or OMP. The hypotenuse PO of the right triangle OPM is equals to 5. This is the radius of the semicircle. We just right now found out that side OM equals to 3 units itself. Side PM is the missing side. Here by PT, the permission for Pythagoras theorem. So actually, this is the right triangle OPM. This is a point from the original domain. According to the Pythagoras theorem, this right triangle OPM, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. So I write it down. PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. The hypotenuse PO equals to 5, therefore PO squared is 5 squared, that is 25. and it is equal to PM square. PM is the missing sign, so electricity, so it is PM square plus OM square. OM is 3, therefore OM square is 3 squared, that is 9. So in total we should find out that 25 equals to PM square plus 9. Here we'll subtract 9 from this equation, and we get that PM square equals to 25 minus 9 is 16. PM square equals to 16. Here we take a root out of this equation, and we get that PM equals to the square root of 16, that is 4. PM equals to 4 units in itself. This is the missing side PM that equals to 4 units in itself. In the next step, I'll copy the right big triangle APM in a new page, and we'll implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Side AM equals to 8 units in its length. The hypotenuse PA equals to X units in its length. That is the 9th segment that we are looking for in this question. So actually, this is the right triangle APM that I go between the original domain. According to the Pythagoras theorem, in this right triangle APM, PA squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. So I write it down. PA square or AP square, that is the square of the hypotenuse, equals to PM square plus AM square. The hypotenuse AP equals to X units in its length, therefore AP square is X squared, and it is equals to PM square. PM is 4, therefore PM square is 4 squared, that is 16. Plus AM square. AM equals to 8 units in its length, therefore AM square is 8 squared, that is 64. So in total we should find out that X squared equals to 16 plus 64, that is 80. So X squared equals to 80. We substitute 80 by 16 times 5. So X squared equals to 16 times 5. Here we take a root out of this equation, and finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only 5. So in total, we found out that the last segment that we're looking for, X, is equals to either 4 times square root of 5, 4 times square root of 5 also equals to 8.94 units. So actually, in both methods, we found out that the length of line segment AP is equal to X. It is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equal to X is equal to 8.94 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our test was to find out the area of this green shape. So in the domain, we have a semicircle. We know that BC, that is the diameter of the semicircle, equals to 10 units in its length. We also know that PEC equals to 8 units in its length. This is angle ABC, this is the right angle. Again, our test was to find out the area of this green shape. So first of all, we join points B and B together by straight line. By joining points B and B, we created peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of this semicircle, and therefore according to rule 5, any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. Therefore peripheral angle BPC must be equal to 90 degrees in its size according to rule 5. The next step, we implemented the Pythagoras theorem on the right triangle BPC. The diameter of this, the hypotenuse of the right triangle BPC is BC. Therefore, the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. Again, the right triangle BPC according to the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. The hypotenuse is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to PB square plus PC square. BC is 10, therefore BC square is 10 square, that is 100, plus PB square. PB is the missing side, so relative it is, plus PC square. PC equals to 8 units in its length, and only to what is given as the question, therefore PC square is 8 square, that is 64. So in total, 100 equals to PB square plus 64. Here we subtracted 64 from this equation, and finally found out that PB square equals to 100 minus 64 is 36. PB square equals to 36, we took out of this equation and finally found out that PB equals to the square root of 36, that is 6. So the missing side, this missing side PB equals to 6 units in its length. It is given us the question that AC is a straight line. So if you focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. According to rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AC at point P? We have this angle, that is the right angle. So the right angle plus this missing angle in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right angle APB we define angle ABAP, this angle is alpha. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. It is given us a question that the big angle ABC is equal to 90 degrees in its size. So, therefore, this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is equal to 90 degrees. This is the size of the big angle ABC. So this missing angle must be equal to alpha. This angle equals to alpha. This angle equals to 90 degrees. And therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. In the next step, we prove that the right triangle APB similar to the right triangle BPC according to angle similarity rule. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the three angles of the right triangle APB are correspondingly equal to all the three angles of the right triangle PBC, therefore those two right angles are similar to each other according to angle similarity rule. Repeat again, if you found out that the right triangle PBC is similar to the right triangle APB according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle APB over side BC of the right triangle BPC is equal to side AP of the right triangle APB over side PB of the right triangle PBC. PB is the common side that belongs to both triangles, and also we derive that is equal to side PB of the right triangle APB or side PC of the right triangle PBC. Repeat again. If we found out that AB over BC equals to AP over PB equals to PB over PC. Actually, in the numerators of each expression we have the size of the entire APB. In the denominator of each expression we have the size of this entire PBC. So found out that AB over BC equals to AP over PB equals to PB over PC. AB is the missing side, so we leave this it is. BC is 10. AP is the missing side, so we leave this it is. PB equals to 6 units in strength, according to what we have already found out. PB, again, here is also 6. Over PC. PC equals to 8 units in strength, according to what is given as the question. So in total, we found out that AB over 10 equals to AP over 6 equals to 6/8. Those two sides or those two expressions are equal to each other. Therefore, we get the first question from those two expressions. According to the first question, AB over 10 equals to 6/8. AB over 10 equals to 6/8. Here we multiply this equation by 10 and finally found out that AB equals to 10 times 6, that is 60 over 8. Here we divided both the numerator and the denominator of this number by 4. 60 over 4 is 15 and 8 over 4 is 2. So in total AB equals to 15 halves. This is that AB is equals to 15 halves. We continue to focus on the long equation. Those two sides are also equal to each other. Therefore we get the second equation from those two expressions. According to the second equation, AP over 6 equals to 6/8. Repeat again, according to the second equation, we have found out that AP over 6 equals to 6/8. Here we multiplied this equation by 6 and found out actually, again, AP over 6 equals to 6/8. We multiplied this equation by 6 and finally found out that AP equals to 6 times 6 is 36/8. Here we divided both the numerator and the denominator of this number by 4. 36 over 4 is 9 and 8 over 4 is 2. So in total we actually found out that AP equals to 9 halves. This is the is inside AP, this is equals to 9 halves units in its length. We defined this angle POB as theta. In the next step, I actually presented the law of cosines, and we implemented the law of cosines in this triangle POB. Actually, the law of cosines is true in any triangle. This is a triangle ABC that could be any triangle. The length of side AB is A, the length of side AC is B, and the length of side BC is C. This is angle BAC, this is equal to theta degrees in its size. According to the law of cosines, this triangle ABC that could be any triangle, the following equation is true, that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. We implemented the law of cosines, this triangle POB. According to the law of cosines, in this triangle POB, the following equation is true, that cosine theta equals to 5 squared plus 5 squared minus 6, 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. And again, according to the law of cosines, in this triangle POB, the following equation is true, that cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. 5 squared is 25. Plus 5 squared, that is 25, 25 plus 25 is 50, minus 6 squared, that is 36, so 50 minus 36 is 14, over 2 times 5 times 5 is 50, so in total we should find out that cosine theta equals to 14 over 50. We would like to find out the value of theta itself. We operated the function cosine on theta and the result is 14 over 50. So, we do an example how to find out the value of theta itself. We know that the root is the function of the square. if we take number 3 and we square it, that is to say, we operate the operation of square on 3, 3 squared is 9. Now we would like to get number 3 again. How we can find number 3 again? We just have to operate the opposite function of the square, that is the root, on the result 9. In this way you get the origin number 3. Why? Because the square root of 9 is 3. So actually the inverse function cancels out the operation of the function. In this way you get the origin number again. It could be the origin number, or it could be also the origin angle. So in order to find out the value of theta itself, actually we operated the function cosine on angle theta, and the result is 14/50. In order to find out the value of theta itself, we just have to operate the opposite function of cosine on the result 14/50. The opposite function of cosine is arc cosine, so we have to operate arc cosine on the result 14/50, and the result will be angle theta itself. Why the result will be angle theta itself? Because the opposite function arc cosine cancels out the operation of cosine. Again, the opposite function of cosine, that is arc cosine, cancels out the operation of cosine. For that reason, arc cosine of the result 14/50 will be equal to theta itself. And arc cosine of 14/50 is 73.74 degrees in its size. Actually, you can find out the value of arc cosine of 14/50 by using any scientific calculator. So arc cosine of 14/50 is 73.74 degrees. That is the value of theta itself. So actually found out that the value of theta is 73.74 degrees. Our task is to find out the area of this green shape. In order to find out the area of this green shape, we have to find out the area of this segment VP. What is the area of this segment VP? Actually, from the drawing, it is very easy to see that the area of segment BB equals to the area of sector BOP minus the area of this triangle BPO. Again, the area of this segment BP equals to the area of sector BPO minus the area of triangle BPO. And again, the area of segment BP must be equal to the area of sector BOP minus the area of triangle BOP. What is a sector? A sector is a portion of a circle with two radii and the arc between them. And again, the green shape AOB is a sector. Sector AOB consists of two radii and the arc AB between the two radii. The angle between the two radii is theta. It is also defined as the angle between the legs of the sector AOB. The area of this sector AOB must be equal to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. I repeat again, the area of the sector AOB equals to pi r squared, that is the area of the sector, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So we'll implement a new rule in order to find out the area of this sector BOP. The area of sector BOP must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees, over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, pi r squared is 25 pi, times 73.74 degrees over 360 degrees. In total, the value of this expression is 16.088 square units. So if you found out that the area of this sector BOP equals to 16.088 square units in its size, minus the area of this triangle BOP. Triangle BOP is an associated triangle because side BO equals to side PO equals to 5. In order to find out the area of this associated triangle POB, you just have to, from the vertex O, go perpendicular on the base PB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and the base PB. This point is point M. We have the rule that the perpendicular to the base of an associated triangle bisect the base. So the perpendicular OM to the associated triangle OPM, or the perpendicular OM to the base PB bisect base PB. PB is 6, therefore half of 6 is 3. So PM, the first half PM is 3 and the second half MB is also 3. And there of this associated triangle OPB must be equal to the base PB times the height MO over 2. There of this triangle OPB equals to the base PB times the height OM over 2. PB is 6, OM, in order to find out the level of OM, we just have to operate, implement the Pythagoras theorem on the small line diagram POM. According to the Pythagoras theorem, on this small line diagram POM, 5 square minus 3 square equals to OM square. 5 square is 25, minus 3 square, that is 9, 25 minus 9 is 16, so 16 equals to OM square according to the Pythagoras theorem. Here we took root out of this equation and found out that OM equals to the square root of 16, that is 4. So OM equals to 4 units in its length. So PB is 6, OM is 4 divided by 2. 4 over 2 is 2 and 2 times 16 is 12. So in total we found out that the area of this associated triangle POB is equal to 12 square units in its size. So in total the area of second PB equals to 16.088 minus 12, that is 4.088 square units in its size. The area of the second PB equals to 4.088 square units in its size. Our task is to find out the area of this green shape. The area of this green shape will be equal to the area of the right triangle APB minus the area of the 7BB. Because again, the area of the green shape equals to the area of the right triangle APB minus the area of 7PB. The area of this right triangle APB equals to the base AP times the height of the base PB over 2. AP times PB over 2. AP is 4.5, PB is 6 divided by 2. 6 over 2 is 3, and 3 times 4.5 is 13.5 square units. So the area of this right triangle APB is equal to 14.5 square units in its size. Minus the area of 7PB. We already found out that the area of 7PB equals to 4.088 square units in its size. And 13.5 minus 4.088 is 9.412 square units. So in total, we found out that the area of the green shape equals to 9.412 square units. Repeat again, we actually found out that the area of this green shape equals to 9.412 square units in its size. So we finish with the first question. In the next step, I present the second question, and we solve the second question by using two different methods. Our task in the first question is to find out the length of this line 7AP is equal to x. We have to find out the value of x. In the domain, we have a semicircle. AB equals to 10, that is to say the diameter of this semicircle equals to 10, therefore the radius must be equal to 5. In addition, we know that BC equals to 6 units in its length. AP equals to PC equals to x. Again, our task is to find out the length of AP is equals to x. So we have to find out the value of x. In the first step, we define the center of this semicircle. This point is point O. OA is the radius of this semicircle, that is equals to 10 over 2, that is 5. AB is the diameter, that is 10. Therefore, the radius is 5. OB is also the radius, that is 5. We join points on P together by straight line. OP is also the radius, that is 5. By doing all those constructions, we can do the associated triangle POA. triangle POA is an isosceles triangle because side OP equals to side OA equals to 5. So in the isosceles triangle POA, if you focus on those two sides that are equal to each other, in front of those equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be equal to each other on their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle APO, alpha plus alpha is 2 alpha, and therefore this perpendicular angle must be equal to 180 degrees minus 2 alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle APC is an associated triangle because AP equals to PC equals to X. So in the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. The size of this angle is alpha. Therefore, the size of this angle must be also equal to alpha because they must be equal to each other. So, in the big associated triangle APC, alpha plus alpha is 2 alpha. Therefore, this perpendicular angle must be equal to 180 degrees minus 2 alpha according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copy the right associated triangle APC and the small associated triangle APO in a new page, and we prove that those two associated triangles are similar to each other according to angle similarity rule. So actually, those are the two associated triangles that are copied from the original drawing. This is the associated triangle APC, and this is the small associated triangle APO. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So if you found out that all the triangles of the big associated triangle APC are correspondingly equal to all the triangles of the small associated triangle APO. Therefore, those two associated triangles are similar to each other according to angle similarity rule. And for the fact that those two associated triangles are similar to each other, we will derive that the following relationship exists between their sides. Before that, AC in total equals to 10 plus 6, that is 16. So side AC of the associated triangle APC equals to 16 units in itself. From the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big associated triangle APC over side AP of the small associated triangle APO is equal to side PC of the big associated triangle APC over side PO of the small associated triangle APO. Okay. AC is 16, AP is X, and it is equals to PC. PC is also X over PO. PO equals to 5 units in itself. It is the radius of the semicircle. So in total, we should found out that 16 over X equals to X over 5. If we cross multiply this equation, and finally found out that X times X is X squared equals to 16 times 5. Here we took a root out of this equation and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, inside the root we left only with 5. So in total we found out that X equals to either 4 times square root of 5, or in terms of numbers, 4 times square root of 5 is 8.94 units. And again we found out that the length of this line 7AP that is equal to X, it is equal to either 4 times square root of 5 units, or in terms of numbers, AP that is equal to X is equal to 8.94 units. So we finished with the first method. In the next step, I presented to you how to find out the length of AP, it is equal to X, according to the second method. In the second method, we use the rule that we have already used in the first question. According to the rule, the perpendicular to the base of an associated triangle bisect the base. Triangle APC is an associated triangle because AP equals to PC equals to X. So from point P, we do perpendicular on the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and the base AC. This point is point M. According to the rule that I mentioned, the perpendicular PM bisect the base AC. AC in total is 16, so each half must be equal to 8. The first half AM is 8, the second half MC is also 8. AM equals to 8, so the radius of this semicircle is 5 because the diameter is 10. OP is the radius, this is 5. OB is also the radius, this is 5. And OA is also the radius, this is 5. So what is the length of this small line segment OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. OM equals to AM, that is 8, minus AO, that is 5. So in total, OM equals to 8 minus 5, that is 3. So the length of this small line segment OM is 3. The next step, I copied the right triangle APO in a new page and we implemented the Pythagoras theorem on this right small triangle APO. This is the right small triangle APO that I copied from the original drawing. According to the Pythagoras theorem, in this right small triangle APO, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to PM squared. PM is the missing sign, so we leave this it is, plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we should find out that 25 equals to PM squared plus 9. Here we subtracted 9 from this equation, and finally found out that PM squared equals to 25 minus 9 is 16. So PM squared equals to 16. Here we took a root out of this equation and finally found out that PM equals to the square root of 16, that is 4. So this is this inside PM that equals to 4 units in its length. In the next step I copied the right big triangle APM in a new page and implemented the Pythagoras theorem on this right big triangle APM. This is the big right triangle APM that I copied from the original drawing. AP is the hypotenuse of this right triangle that is equal to x. X is the line segment that we are looking for in this question. We just right now found out that PM equals to 4 and AM equals to 8. According to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. AP is x, therefore AP squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 60. AM squared is 8 squared, that is 64. So in total, x squared equals to 16 plus 64, that is 80. AM squared equals to x squared equals to 80. Here we substituted 80 by 16 times 5. X squared equals to 16 times 5. Here we took a root out of this equation and finally found out that x equals to the square root of 16 times 5. The square root of 16 is 4. So inside the root we left only 5. So in both methods, we actually found out that the length of this line segment AP that is equals to x, it is equal to either 4 times square root of 5 units, or in terms of numbers, AP that is equals to x is equal to 8.94 units in its length. Okay, thank you very much.